Okay, let's start. So, welcome to this session on online algorithms. So we'll start with a talk by Svensson. It's about learning-augmented online algorithms and the Primal-Dual methods.
Okay, thank you very much. Okay, thanks. So this is joint work with Etienne Damas and Andreas Maggiori at IPFL. So please feel free to interrupt me at any point of time. So Roy did a lot of the legwork. We will see the same primal dual algorithm, and then we will do a small twist in this talk. Okay. So not the same. Okay. So I meant it as a. Okay. So learning went online. So online algorithms. So I have this nice example. So you go to Google, you search best graduate school. You wait and you get some returns and everything and everything makes sense except the first ad, which is which has then been like signed by an ad allocation algorithm. Okay, that's the motivation. So here we have the advertisers, and then you have search coming online. Before seeing the future, you need to make an assignment. Okay, see here. So Rivella is the Swiss soft drink. It's after you like it after a couple of years. I like it now. So it's like it's an acquired taste. If you come to Switzerland, try it a couple of times. It's pretty interesting. So and maybe someone search for furniture, we match it to IKEA. Okay, so this is instance arrive online. We have to make immediate irrevocable decisions. Okay, so when we evaluate online analysis, right? So we are analyzing with respect to C competitivity. So if I have, the cost of solution should be at most C times opt. Sometimes there's an additive, set of term. And if it's maximized, it's at least C times opt. So yes, we will come back to ski rental. So everybody is on board. I'm at the beginning of each day, you have to decide you're going to buy or rent. And you will ski an unknown number of days. And the cost of buying is B. And here the difficulty is that we don't know the number of days we're going to ski. So here, probably right, the optimal strategy is to rent the first B minus 1 days and then buy at the beginning of day B. And this is a 2 competitive ratio. Okay, so if you do deterministic algorithms, you cannot do better than 2. If you do randomized, it's like E over E minus 1. So the reason that it's 2 is that if you ski at most B minus 1 days, then it's actually optimal, right? Then the right strategy was to rent, and you rented. And if you ski at least B days, we pay 2B minus 1, whereas opt would have paid B. Okay, so that's 2 competitive. So now maybe you're not happy to have 1 minus 1 or E competitive or 2 competitive algorithm for the matching problem if you're Google. And maybe one reason that we have like not so good guarantees is that it's for any input sequence. Okay, so one way of dealing with this is, of course, as we saw this morning, is to have a random order and to weaken that verse a little bit. Okay, so today we're going to see another way, which is like motivated that you could actually expect the input to have some structure. So to motivate this, like I looked at Premier League searches in the UK. So here's the graph when people in the UK search for Premier League. So that's like the Bundesliga of the UK, which is the soccer. So you see there is some peaks that is pretty easy to predict, and this is the Sundays. Okay, so you would expect that if you allocate ads for football, it's not too hard to see what to do. Okay, so that's ML. I don't know much about it. So so it's like excellent on a normal day, but there's no worst case guarantee. So maybe it outputs an infeasible solution, for example. Okay, so that's like and to say like yes, that it looks easy. I didn't make this up, but if you extrapolate a little bit, the people decide to not search Premier League one Sunday. So I don't know. So there's one Sunday missing here. So this is also Sundays. Any ideas why the British didn't search for Premier League?
It was a break for the national team.
What?
Break for the national team.
Initial LP.
A break. It was a break for the national team.
Yeah, fantastic. Amazing. Who was this?
Andrea.
Oh, fantastic. Okay. Italian. Yes. Yeah, so this is because there's the World Cup qualifiers. So people are like searching about the international games. Okay. So this brings us to Learning-Augmented. So this is like, the idea is All right, so online IAMs, great worst case guarantees, but not so good in typical instances. ML, no worst case guarantees, but good for typical. So then can we get both, the best of the both worlds? Okay. So basically the idea is the following. So let's do an online algorithm, but additionally to the traditional model, you have access to some predictor. Okay, so that tells you what the predictor thinks about the future. And maybe a key thing here is that there's no assumptions on the predictor because we have no understanding of how the predictor makes the prediction. So we don't want to make any assumptions if it's good or bad. Okay, so now the kind of guarantees you can hope for when you make no assumptions on the predictor, I guess the natural one are as follows. So you can be consistent. That means that I made no assumptions, right? But if the predictor turns out to be correct, I would like to do well. Okay, so if the predictions were useful at hindsight, I should have used them in a good way. So then I want to be close to the optimal. Then I want to have robustness, meaning if the predictor goes crazy, even adversarially, I want to bound the damage down. Okay, so I want to be close to the worst case guarantee we had before without having the predictor. And then one thing that I will not deal with in talk about in this talk, but this is of course, you want to have like, you have some error metric in your predictor, right? You don't want to go resort to worst case bounds if it's wrong a little bit. Okay, so you want to have some smoothness that you are like, you guarantee like the case in a nice way as a function of how bad the predictor is. Okay, but I will focus on consistency and robustness here. Okay, so for us to make a case, let's look at ski rental. So now it's the same problem as before, but in addition to this normal ski rental, we also given a prediction P of the number of days we're going to ski. Okay, so now if you're completely not trusting the predictor, well, you cannot do better than 2. So that's bad consistency. If you're completely trusting the predictor says maybe that you should ski 10 B days. So you buy at day 0. But in reality, you only skied 1 day. So that's terrible news. Okay, so you have a bad robustness. Okay, so it's like you know, one to completely trust or not trust is not a good idea. So what would be a reasonable algorithm? Any ideas how you would use the predictor? Like, okay, no ideas. Okay, so basically, so you can balance. So you have basically a parameter lambda, how willing you are to trust, and basically you weight lambda B days to buy if prediction is to buy, and this will actually gives you consistency 1 plus lambda and robustness 1 over lambda. Okay, so this means that if you put like lambda to be 0.1, you're not too bad if the predictor was right, and you are bounded damage if you go completely crazy. And this is just to say that there is an interesting trade-off even in a ski rental that you cannot do, trivial stuff. It's kind of simple, but I mean, not straightforward. Yes.
B is P equal to B plus.
So if
the
P.
prediction is P days.
Yeah.
And you weight lambda B.
No, lambda B. So I mean, basically here the only value of the prediction we're gonna use is whether you should buy or not. So if the prediction is less than B, you should rent, right? If the prediction is more than B, you should buy. And if the predictor says that you should buy, now I don't know if I did this wrong, but now if the prediction says that you should buy, you shouldn't buy at day 0. Because this puts you at a big risk, right? You're trusting the predictor a lot. So just to hedge your bets a little bit, wait lambda B days to buy. Okay. Okay, so this is not my idea to look at this. So in fact, they were ahead of their time. So Madjan Nasazadeh Sabir in EC 2007 already looked at this framework for ad allocation. Okay, but they didn't call it Learning-Augmented, and as I said, it was ahead of the time. So in an independent work, like in 2018, Likos and Vasilevsky also studied this under the Learning-Augmented framework in competitive caching, and since then it has completely gone crazy with tons of papers on all. Once you have this nice theory framework, you can revisit your favorite problems in online algorithms. And it's not actually now also very interesting is that you can actually analyze warm start, a little bit what Jens was talking about in his algorithm, right? It seemed not work with Jens' case, but for example, people have done it for Hungarian method. Can you estimate the duals to speed up Hungarian method when you have some knowledge about instances? Okay, so what we did is that we were reading this book about Primal-Dual approach for online algorithms. And then it was like, can we actually do something about this framework to adapt it to when we have predictions? Okay, and we will see that there's a small set twist you can do to this method, and this will recover some tight trade-offs and get some new results. Okay, so let's look at the SetCar problem as we saw. So I will not care about the rounding problem that we saw this morning. I will only care about calculating a fractional solution. So here in this question, right, we have an unknown ground set. We know the sets in advance, but then the elements arrive on a line. And when an element arrives, I will not require you to integrally cover that element. You have to fractionally cover it. Okay, so in other words, when an element arrives, I get the constraint. I need to cover it with the sets that cover that elements, and I need to cover it fractionally. And I need to monotonically increase my sets. So here's an example. This element arrives, the yellow star. You know, maybe I cover it by setting xs1 and xs2 to be 1/2. Both that will cover this element fractionally. Now another element arrives. Oh, I need to push up xs2 to be 1. So I covered that. So I have to always increase. I'm not allowed to say, oh, actually, I should have not picked this. Oh, sorry, I shouldn't have picked this set. I'm not allowed to lower afterwards. Okay. And the goal here we would pay 1.5 and of course op pays 1. So now there's a famous difficult instance, right? You can imagine like the first constraint says, hey, all the sets can cover this item. What are you supposed to do? Yes. No, I'm only so here there's no guessing, right? Because it's a fractional solution. So, you know, I don't need to use randomness because, you know, and so fantastic. So I put 1/m everywhere. That seems like a suitable strategy. Now, of course, I drop the first. I have a new element that's only covered by S2 to Sm. Now, what is a sensible strategy is just to push them up to 1/m minus 1. And this continues like that. And you will see that you will get log m, whereas op was 1. Okay. So this is like this is basically, you cannot do better than log m, as we saw this morning. Okay, so now if we had a prediction on the hand, if he predicts Sm, let's just take it and we get 1. So that's good. But again, as in ski rental, it's not great to completely trust the predictor because he could predict S1. If I take that 1, then 2, and so on, right? If you completely trust, I'm even much worse than log m. I would have a cost of m. Okay, so there is some trade-off to be made. All right. So let's look at how to achieve this trade-off with the Primal-Dual approach. And basically what we will do is to take the algorithms from Neves and Seffi's book, and then we'll interpret them a little bit. And then we'll just change small thing using the predictions, and this will help. Okay, so to do this, let's look at the Primal-Dual method for the SetCar problem. So what we said is, you know, now an element arrives, so a constraint arrives. So if the sum of I such that E is in Si, xsi is already bigger than 1, as we saw in this morning, life is good, right? The element is already covered, so then we do nothing. Okay. Otherwise, we have to increase the variables that cover this element. And the way we do that is, you know, for each of these guys in the constraint, we update it by multiplying by 2. And then I will add the term here instead of initializers. I will take 1 over the number of sets covering E. Okay, so this additive term will make sure that I will satisfy the constraint, right? For each set that covers the newly arrived element, I add 1 over the number of sets covering that. Okay, so and now for bookkeeping, I will add E to be 1. Okay, but as said in this morning, I don't need to. That's just for bookkeeping the dual. Okay, so that's the whole algorithm in the Primal-Dual framework. And the analysis, yes, example, here I have one guy arriving. I will initialize with 0 values, right? So now I put 1/3 on each set, 1 over the number of sets covering this element. Now maybe a new guy arrives. Now, this guy sum up to 2/3. I need to increase them. I'm sloppy, so I might I set them to 7/6. Here we don't care about the constant, so let's be a little bit sloppy. And so on. Okay, so that's that. So now the analysis, you see that every time we increase the primal, we increase the primal by at most 2, and we increase the dual by 1. So this means that, the dual infeasible solution we will construct is a multi-factor 2 from the primal. And then we have to prove that y scaled down by log m is a feasible solution. To see that is that we look at the constraint of the dual, and every time we update the ye variable in this constraint, we have doubled the variable xsi. Okay, we double that variable every time we update the ye variable in that constraint. We can double it at most log m times, right? Because we set it to be one of the number of sets covering. Okay. So that's the analysis. But I go a little bit quick here because that is not important for us. Okay, so this shows that it's a log m. It's beautiful. That's, I guess, why both I and Roy talked about this, because so clean and nice. Okay, so now we wanted to incorporate predictions. And I claim if we just look at this method, there's a fairly easy way of doing that. All right, so think about this guy arriving. There's 4 sets possibly covering him, right? So in this method, you added a uniform additive term. Okay, you said 1/4 to this guy. Okay, 1/4 to everybody. What's the interpretation of this? I have no idea about the future, so I want to hedge my bets uniformly, right? All these sets can be equally useful for the future. So let's just put 1/4 and spread equally the fractional value. But if I have a prediction that tells me which set to use, right? I should not spread it uniformly. I should take that set. Okay. Now we shouldn't trust it blindly. So what we do is, we put lambda. We have this lambda trusting parameter. So if lambda is 0, we completely trust the predictor. If lambda is 1, we go back to what we had before. So here we just say, hey, we do sets covering E, but we increase the guys that are covered in by the predictor even more aggressively, so by 1 minus lambda. So, for example,
what is the predictor really giving you?
Yeah, so here it's into the, but you can think of it in online telling you which sets to use to cover this element.
Okay.
So, so if the prediction says S3 here, what would the impact be? Well, we would put XS3 to be like 1 minus lambda plus lambda/4, and the other ones to be lambda/4. So you see, if lambda is 0, we would completely trust the predictor, and if lambda is 1, it would be uniform like before. So it's just, yes?
Just to confirm, the benchmark we're thinking about the predictor is if we only do what the predictor says, the predictor is not saying something like relative to what we've done so far.
No, exactly. So the predictor we can think of here as, here it doesn't make much, but he, even at day 0, he tells us like an optimal solution. He doesn't need to adapt it. All right, so now analysis. If you just redo exactly, well, actually this is just a shortening argument. So because we increase the good variables very aggressively, right, depending on this lambda. So, if the predictor is correct, it will be 1/1 minus lambda competitive times some constants. And by redoing the analysis I tried to explain before, you get a robustness that is log m over lambda. So it's not too bad, right? I could put lambda to be 1/2, then I get a constant competitive algorithm if the predictor is good, and still a log m competitive if it's bad. So here we lose just in the constants. Okay, so that's good. And now the general recipes, right? Just formulate the LP relaxation or look in the
question. Can you remind us what was the predictor predicting in the SetCar in the previous?
Think of him at day 0 telling you the sets in the optimal solution.
Okay, thank you.
So we look at the Primal-Dual method and we basically tweak the rates that, yes. Yes. Yes, there's a big O around the consistency. Probably. Yeah. You're right. Probably right. I will come because I will remove the big O. I have to, probably you're right. That would be easier. Thanks. But we will we will remove the big old slacker list in just a slide. Not for set cover though, so probably you're right. That's embarrassing. No. No, you cannot, right? Because then in the consistency, you will still pay log m. So you have to do something smart, right? You need to hedge your bets for the future. You cannot just run the online. Yes, but it's like too competitive. I cannot afford to run the online log m competitive algorithm in parallel. Yeah. Okay. Okay. So simple answer. So now let's remove these constants. So let's look at ski rental. So now your prediction is if you're going to buy or not, or how many days you're going to ski. So now you look at the Primal-Dual algorithm in the book, and you see, well, you don't see, but it's not important. So basically, I don't want you to understand exactly. There is a Primal-Dual algorithm for ski rental. If you look at this algorithm, it looks exactly, it's a coverage problem. It looks exactly like set cover. There's an additive term that you add when you have to fix the constraint. You will just, the change when you have predictions is just to change the speed you do this rate depending on the prediction, okay? Exactly the details here I didn't want, so that's why it's small, but this actually recovers exactly the right guarantees, okay? So this recovers the trade-off between robustness and consistency that is completely tight for a ski rental. And you can also do generalizations like TCP acknowledgement, where what's the definition? Okay, so server receives a stream of packets. So you have a package, and then you need to acknowledge. So yes, there was packages, and you need some acknowledgement. Okay, so now the cost function is the number of acknowledgements you send. But you can also wait to send an acknowledgement, but then you have a price to pay that you're delaying to send an acknowledgement for a package. Okay, so that's a theory question, you know. So I have sent packages. I can either send acknowledgement after each package. I pay no delay cost, but I pay many acknowledgements, or I can wait and I pay some linear holding cost. And here you can do exactly the same. So you look at the Primal-Dual algorithm without predictions. There is, if you think about it, so there is exactly some additive term adds. You just replace this using the predictions to have a little bit more aggressive updates if you have predictions, and less aggressive if it doesn't correspond to predictions. And you will recover exactly these consistency and robustness guarantees. Okay. So that was a little bit what I want to do. Yes, so actually, so what is nice is that you can actually run experiments on this, and here it's with a distribution for packages, and one can see a little bit what's going on. So this replacement rate is basically how well does the prediction correspond to the reality. So when the predictions are accurate, of course, setting a small lambda parameter leads to better costs. But then when the predictions are nonsense, setting a small lambda parameter penalizes a little bit the worst case guarantee. But you can, like, what is kind of nice, we did a scheduling as well. Like there, you can use very simple predictions, like the day before predicts this day. It leads to much better online performance, at least on those instances. Okay, so maybe I wanted to, so here we unified some of the previous results and got some new with simple proofs by just extending Primal-Dual. So some new directions is, you know, this was already done. So with packing constraints to some problems. Then it would be nice to do to non-linear objectives. So, you know, many of these online questions with speed scaling to minimize energy, for example, have quadratic or even like higher, like cubic objectives. And then I like this question we have tried to understand a little bit better, is that all the work so far is kind of weird. They have assumed that advice comes for free. So, you know, you have a caching algorithm and you ask for advice, you better be able to calculate that advice quickly. So, you know, what if the advice doesn't come for free? So how much do you need to ask for advice in order to get a good guarantee? So like for TCP acknowledgement, we have an advice for each package. So like, when should we send the next acknowledgement? Is that really necessary? Or can you like decrease the number of times you have to listen or calculate some prediction? Okay, so thank you.